So thank you for being here today, folks. My name is Bruno Emmer. I'm here with my colleague Byron Arneo. We are both solutions architects at the Critical Capabilities team. And today we're going to talk about how customers can leverage specific architectural patterns to reduce the area of impact and survive to difficult days. Right? I just want to be mindful that this session is going to get very academic, and it's a 300 level session, so we won't be talking about some networking concepts or even services. We are really focusing on architectural patterns on this session here.
So this is a little bit of an experiment we've invited you to today. So this is basically, we're going to conduct this workshop as a format of which the two of us, when we were thinking about doing this, the conversation that we were having. And so we're going to be taking a little bit of the roles of what we hear customers typically talk about and some of the challenges and things that you should be thinking about when you're thinking about isolation in this way. So with that being said, at AWS, embedded in our culture is this notion of things will fail all the time. You've seen this slide, probably if you've been here through the week. This has come up in a couple different places. So this is at the very heart of what we do in AWS. Hopefully through today, you're going to learn enough where failures or impacts that you see will not be impacts in your company. First, I want to think about, or just generally think about the categories of failure, right? So these go, and there's a lot of these things that you should probably recognize, right? So we think about code deployments and configuration. And so these are the typical things that you'd see from bad code deployments, from application misconfiguration, those type of things. And recognize, right, when we're thinking about hardware and those type of problems, right, we're definitely not thinking about the type of issues that, where they start out in the beginning where you might have some hardware failures and it goes through the middle in which it runs great. And then at the end, of course, it starts to burn out. And so you end up having that problem in which that it starts to fail. Data and state type of issues, the second category that I'm sort of showing here, is typically going to be when you have stale data caches, misconfiguration, you'll have out of memory that you might have in instances, those type of problems, those categories of things. And then you have things like third-party type of things. So you can think about other services or workloads in your organization that you're dependent upon. Think about the news feeds or other parts for applications that you have. Those type of problems are the ones that you'll generally sort of think about in there. And then core infrastructure, right? We know what those are, right? Those rack failures, infrastructure stuff, things of that nature that are kind of network data center issues, et cetera. And then, of course, we have highly unlikely scenarios. And you guys have seen a few pictures of these, and think about things like, when we're talking about meteor strikes, whole region failures, power grid issues, et cetera, things of that nature. So with all of those being said, when we think about the various causes for these, right? The things off to the left here are the things that we design for high availability, right? These are the things like whether it's operator errors, which we're talking about bad code deployments, component host failures, entire rack failures, those type of things. And then we think about things like on the other side here, which are really where we do our DR type of discoveries, right? Most customers really sort of focus on, this is longer term type of issues where total internet failure, regional failures, et cetera, things of that nature, right? So those are very unlikely to happen, right? So those are more rare.
Yeah, so Byron, I guess that what you've been saying is really the way for us to think about failures is to try to anticipate them, right? And those categories helps us to get to that point, right? Mm-hmm. But I guess that then the question really becomes how do we protect ourselves against those failures? What are the mechanisms or the way of thinking for us to get there?
Yeah, so good question. And so the ones that are up on the top, right? A lot of customers think about, they're all check green. These are the ones that commonly we know about, right? Rack down, we have auto-scaling groups for that. AZ impairments, those type of things, again, you can sort of deal with multi-AZ deployments. Regional failovers can deal with regional impairments, right? But the ones that are on the bottom, like the bad deployments, human failures, and poison pills, which some customers know as black swan kind of events, where you've got a SQL injection or something of bad code, something that goes and knocks out a system. Those are the ones that really are difficult to fully mitigate.
Yeah, so again, taking from that standpoint, right, and thinking about those failures and how hard it is to mitigate, I guess then, again, it just triggers another question, which is, what happens when a workload becomes too big or actually really too important to fail, right? For these most critical applications that we talk about.
Yeah, so good question here. So let's talk about a real world scenario to start with, right? So we've got plenty of people that have these critical hyperscaling type of applications in which they sort of become too big to test. This is not really the type of thing that necessarily every workload is going to necessarily have to have this type of isolation with. But for the most critical ones, it takes a long time to test at scale, right? And so when we think about that, and how do we do this today, right?
Well, I guess that this is really like about understanding the challenges, right? And again, as Byron was saying, we do have like a lot of failure modes, and there are like mitigations like in place for us to start thinking about it. And talking about architecture, right? It's really understanding the journey and kind of like what we have in place nowadays, right? So most of the applications that we are usually seeing, like they rely on those like traditional enterprise recovery strategies. So we're mostly talking about like backup, restore practice, right? And this is something like very common, right? But as we start shifting to the cloud and we start shifting to more like advanced like resilience patterns, we'll definitely be thinking much more like, as you mentioned, about high availability, and we'll be talking about like disaster recovery, right? And again, as I mentioned, it's really a matter of like evolving this like through the journey. So usually what we see is like customers starting with like multi-zonal, like so relying on availability zones and implementing like some sort of active, high available implementations, like high available applications, or even like thinking about like multi-zonal failover strategies, right? Then it tends to evolve like even more, and we start getting into like multi-region active deployments, and again, even multi-region like failovers, right? Which is like taking out these boundaries of our regions and like just extrapolating the application through them. And I guess that really the message is thinking about like this kind of like as fundamentals is actually what enables us to start thinking about like more advanced resilience patterns, right? So I guess that this is really like just to set some context on like where the conversation should come from and where it goes to, right? And again, like having that in mind, I think that really getting back, like taking another step back and asking the question again, which is how do we usually protect against those failures that at the beginning were not easy for us to mitigate?
Yeah, so just to sort of review here, in the Wayback Machine, we looked at the ones that were easy to fail, but the ones on the bottom, right, these are the ones that we really need to be able to solve for. So let's think about that from the perspective of bulkhead pattern, right? So we have you have a ship, it's a concept that's borrowed from naval engineering where you have this bulkhead. And the way that it's set up, it's all these internal chambers inside the boat so that if a particular area is impacted where, I don't know, let's say you've hit an iceberg, let's say for example, that the entire boat wouldn't fill up with water, right? And so that prevents the entire ship from sinking. And so that's an isolated failure. That's the type of thing that we're thinking about with that. So with all of that being said, how do we build this in software?
Well, and again, I think that this is a great concept, right? And I feel that this is really when we start talking about the concept of like cell-based architectures, right? But just before we got that, I just want to like ask the audience here, how many of you here in this room have heard about like this notion of cell-based architectures before? All right, cool, thank you. And like from those that actually heard about it, how many of you have this pattern running in your production environments, or really implemented those? All right, I see a few hands there. Would love to catch up with you guys later and kind of like get more knowledge about like what you're doing there, because this is something that we are really interested on, right? But just like moving forward and making sure that we are like baseline, like that we are leveling set like this presentation. The notion of like cell-based architecture, it's kind of like similar to what Byron was talking about when he was mentioning the bulkhead pattern, right? So when we look at like traditional software architectures or like traditional application architectures, we would have like everything being fed and everything being served by pretty much like the infrastructure that we provision, right? So in this example here, we would have really like a load balancer, EC2 instances in a database that would be like acting as a dependency. But the notion of creating this bulkhead really goes over like creating copies or actually different instances of this entire application. And by like the entire application, I really mean like the application and all its dependencies that we actually own, and deploying them individually as we would do with like the bulkhead pattern, right? And this is really like what we would be calling the cells. So when we start like doing this and we start like deploying multiple copies of the entire application, we are actually isolating specific failures, right? Because if something happens to one specific cell, the only ones who will be affected will be the clients or the customers who will actually be tied to that specific cell, right? So you're like really reducing the blast radius of potential failures, right? It's very important though to understand that when it comes about this sort of implementation, data needs to be partitioned, right? We are not talking about replicating data to the cells. Like, remember, one concept is everything needs to live within the cell, including the data that the users or the clients will be consuming, right? And again, this is a way to like offer a complete isolation for that application, right? And again, it also helps us because when we start thinking like around this model, it will actually provide us a predictable scale unit, which in this case are going to be the cells, right? So a few concepts about the cells, right? Just to make sure that this is like very clear. The first thing is cells are meant to provide like workload isolation, right? So this is what we are trying to achieve here. And by having this workload isolation, we will actually be able to like implement this like failure containment, right? So again, as the book head pattern, if there's a problem with one cell, the problem just spans that single cell, not the entire environment, right? It's changing actually the notion of like scale because we start thinking about scaling out versus scaling up, right? It's really the concept. If my workload is getting bigger, if I'm having like more users, more clients, I'll be actually adding more cells. I'm not adding more capacity to the cells, right? And this lends us to the next step, bottom, which is cells will always have a maximum size. So like we're not saying that every cell will be different from the other. The idea is to make them like even, because this will help us with testing and even with the manageability of like this entire environment, right? So again, as we are saying, cells will be reducing the area of impact for those failures, right? And again, how it differs from like traditional environments. If I don't have like the notion of cells, if I just have like this single implementation, this single instance of my whole application and there's a failure, everyone gets impacted. But if I'm thinking about the notion of cells, right, and if there's like a specific failure on that, it's really like a matter of like containing that failure to the specific user group of users or clients, right? So we are like really reducing the impact. It helps us with like potential financial losses because it's not like affecting pretty much everyone. It helps with image for the company, right? Because it's not like big, like necessary. It's not necessarily like a big thing. We are not going like in front page news by saying that the whole application went down, right? It's really changing this perception of how failures will actually affect users and how it actually affects our business, right? But I guess that one thing, Baron, is we are talking about like this isolation between the cells and by copying like this data, right? And having like different like infrastructures, like different instances of that. But when it comes about like access patterns and like sharing this data, kind of like making sure that it's very clear to us like where each user should go to, like how would we think about it?
Yeah, so when we think about it from the standpoint of traditional architectures, right? We typically, and we've been labeled here, I just went through and I labeled them A through H, so to have an idea of these workloads and customers, and we think about the nodes across the bottom. And so today when we have somebody that goes in, and let's just call it workload E, for example, right? And they go through and there's something wrong with that workload, right? And so it ends up poisoning that first node in there, and then you end up having a problem. And so what effectively happens is that node becomes unavailable. So that's not great. And ideally, though, unfortunately, though, you'll end up having that same workload. We talked about that poison pill or that black swan event in which it goes in. And now what we see is a cascading failure that ends up happening across the entire workload. So that's kind of a challenge, right, in that we're taking out everything, and all the workloads at the end of the day are unable to be able to leverage our service.
Yeah, and just kind of like making clear, like when you're talking about this poison pill, it's not necessarily something intentional, right? Like you're also mentioning like retries that are going to be on code and can actually take the infrastructure down, right?
Yep, and you know, with this, and we've all seen this before, we have these cascading failures in the area of impact, right, as much as what we see today, is that we have all clients. So another way of thinking about this problem, though, is to take this and to think about sharding this, right? And so if we take this entire thing and redo this and say, okay, I'm gonna break this up into pieces. So I've not got all 8 of them going after the same set of workload, set of servers, right? But I'm going to break those into pieces. So when we have E today, same problem, same poison pill, same deployment issue coming in. It goes in and, as we said before, breaks that first node in there, and it renders it unavailable. What do we think is going to happen when we do that with the same thing when we go and we add the workload again? Same thing, it's going to end up breaking that second one. But the consequence here is much lower, right? If we look at this from the perspective now, F is going to be affected by this, of course, but none of the other workloads are. And so you'll see across here, when we do this, except for E and F, all the other workloads are the ones that are going to be preserved and be working as we expect them to do. So we think about Yeah. The area of impact for this, just to show, this is clients divided by shards, right? So the more of this, the more shards that you break this into, the less impact ultimately that you'll end up having, right? So with all of that being said, right, this is a real challenge to think about how do you route to all these various cells, right? Because now that's almost like the single point of failure there in a way.
Yeah, and I guess that this is kind of like a natural question that we will end up having, which is when we have this sharding, this distributed users, like and all those requests coming, like how do we know where the request should go to in terms of like cells or like even which shards like the users belong to? And this is why when it comes about like implementing the cell-based architectures or even thinking about like this sharding at the application level, we need to think about implementing a routing mechanism, right? So when we're talking about this routing mechanisms, we're talking about like a really thin layer that will be responsible for like implementing the routing logic, right? And pretty much like the application will start relying on that, right? So I won't say that this is going to make like the application lives like way easier, right? It does introduce some complexity. And this is why this component needs to definitely be very resilient, right? It needs to be running all the time because like all the logic about the routing, like where the request is going to, like how it's going to be handled, like what's the shard, what's the cell that needs to be, like it definitely needs to be handled by this specific component. Right, so the notion is really like keeping this component as simple as we can, right? And this is what we mean like by saying that this is a thin routing layer, right? And by the way, by thin routing layer, I'm just like really talking about a few lines of code, right? Like if we want to like think about the software engineering behind it, it should be a few lines of code, not more than that.
So would you have a database lookup in there as an example?
Ideally not, right? Like we want this to be like ephemeral. Because again, we want to make it like very resilient and we want to reduce the need for like external dependencies for this component, right? And by also like reducing, additionally to reducing like the external dependencies, we also want to make this component statically stable, right? Which in fact means that even if there's like an environment on the infrastructure where this component's running, right? If it's running like across different AZs and then there's like a problem with the that AZ that would affect that component, we would like still, for example, having enough capacity to keep operating, right? So this is really like what this is all about. Right? And when it comes about like ways of implementing this, like there are plenty ways that we can think about like how to implement this like technically and how we can make this like routing mechanism to work. And I'm just going around to talk like very briefly about two of those, right? So a very simple way to think about it is by using a technology like a protocol that's been around for a while, which is DNS, right? Pretty much every application leverages DNS nowadays. The whole internet really relies on DNS, right? So we can think about like just having a routing layer, like building this piece of code that will basically be updating DNS entries, right? And then since we're talking about cells and sharding, we'll provide to each of those users or those clients that are going to those like specific cells, a specific like URL, right? So like each client is responsible for just like requesting, like sending the requests directly where it needs to go, right?
And this is like a much simpler way to approach it in a way because it's not really, as we know, much software that's written for routing and cells. So like this is kind of like using something off the shelf that's getting halfway there.
Yeah, exactly that. Like really the building process for this type of like routing mechanism goes over like building like this piece of software that will actually update those entries at the DNS, right? And then shifting like the control of this traffic back to the clients, right? And it can be like really a good thing if we're talking about like a small number of cells or like probably a small number of like users. But if we start like growing the application a lot and we start growing like the number of cells and growing like the user base, it can get like very complex, right? We will see the management complexity coming with that. Right, and just by an example, right, like if I want to move one user from one cell to the other, I will have to rely on DNS-TTL, I have to send it information back to the client, so I need to be touching that area as well, right? So again, it works well for like simple use cases, but I would say that depending on the complexity, it might not be the good idea, right? And really, since we're talking about these ideas and the complexity, another way of handling this is thinking about like building a cell router that will act pretty much as a load balancer. Right, so the idea here is not like relying on existing protocols. The idea here is building like this entire new layer that will receive all the requests, and then this layer will be responsible for like just sending the traffic where it needs to be, right? So it's really server side. It's not like relying on the clients. Like the clients won't even know that this layer exists, right? But it gives us like full control over like where we need to send the traffic to.
Yeah, and it seems like with something like this, obviously, whereas DNS might have TTLs, things of that nature, this here wouldn't, and so it'd be a little bit more quicker reacting as well.
Yeah, exactly. Like we're
client side.
Exactly, we're really controlling like all the traffic logic on the server side, right? But it doesn't mean that it's going to be simple, to be honest, right? We need to think about like all those concepts that we just explored. We need to think about like making this like very resilient, and there are like a lot of different techniques that we can apply, right? So just as an example of like if I had to build like a routing layer, how I could approach that. One way of thinking would be really like thinking about static stability and thinking about like breaking this routing layer in two different like layers, which would be thinking about the control plane, where I would like implement all the logic, all the new cells, like new users, like pretty much everything. That's kind of like the CRUD operations. I would like send this to the control plane. And then I would just have like a data plane that would be basically receiving this information and routing the requests, right? And by the way, when you start talking about this, like it's really mostly because we understand that the control plane tends to be like much more complex, because this is where you're handling all the logic. This is like where you're really like implementing all the changes, right? So we want to make sure that even if the control plane goes down, the application, the routing wouldn't be impacted, right? And there are like really other mechanisms that we can think about, we can add on top of that to make it even more resilient. We can think about like the constant work pattern. So there are like a bunch of different stuff that we can do to make sure that this component is really like resilient as it needs to be.
And this seems like what we're telling customers all along when we talk about static stability is really to be focused on data plane operations more than to be able to focus on control plane, because we know that control plane can be less reliable.
Yes, exactly. And like they can be less reliable exactly because there are more moving parts, right?
Yep.
There are more moving pieces, so we don't want to be relying on that all the time.
Mm-hmm. Yeah, so what I think I'm getting and what I think about this, and it's really important because I see people get confused on this all the time, is right, cells are not availability zones or regions. And this is an important distinction fact, right? Because I think it's easy with these segmentations. We talk about availability zones and regions as physical isolation boundaries. When we think about things like cells, we're really talking more about logical barriers for isolation, right? And so when we think about it, when I overlay, and I just put this together to sort of like say, okay, if you look at a cell, it can actually, because we still have the same HA, DR kind of considerations that we have. None of that's went away. So we can really have cells that can straddle multiple AZs and multiple regions, right? Because we might have an application, customer saying, okay, this is highly critical, highly scalable, need to be able to have that availability level. So you should be really sort of, cells provide compartmentalization, and you really should be designing for that combination of those things to achieve their reliability goals. And so also, cells are not necessarily used as implicitly as a scaling mechanism. They can be. It helps you to scale, certainly, by being able to have that stability across your entire user base and your customers coming in. But I wouldn't think about this necessarily first if I had, it is really going to depend on the complexity of the workload as to whether I think that this is appropriate for scaling.
Yeah, so basically what you're saying here, like with this statement, Byron, is if my only need is to just scale my application and it's not a critical application to my like business, I might not really even be thinking about like leveraging cells or sharding. I might think about like different practices. That is pretty much it, right?
Yeah.
All right, cool. And just like keep going like on the conversation, because now like we've got the notion of cells, we've got the notion of sharding, right? We talked about this routing layer. We talked about like how we can make this routing layer even like more resilient, right? So this notion of static stability, control plane, data plane. But when I get back to your example, Byron, I really got to a point where initially, without like any sharding, if there was like that poison pill scenario you talked about, it would affect all the customers, right? Mm-hmm. Then we kept going, and we were talking about sharding. But what we saw there is if one problem, like one customer like has a problem, it will actually affect not only that customer, but like more customers that are basically sitting on the same shard, right? So my question really becomes, is there a way for us to make it even more resilient? Are there like any other techniques or like patterns that we can leverage in this space?
I thought you'd never ask. So when we think about the sharding, we went through the example before, and we remember, right, that 25% or 1/4 of the customers were impacted. But maybe there's another way to think about that problem, right? So if we take the same thing where we go through and we say, we want to redistribute this and we want to use something called shuffle sharding. And so what shuffle sharding basically says is that you can take these workloads, but instead of sort of mapping them on a one-to-one basis to each one of the cells, I can map those to different nodes within this farm. And so that their partners or the customers that they're co-resident with or the workloads they're co-resident with are on different nodes in there, right? And so we can continue seeing these are randomly, or you can do this algorithmically or through a hash to be able to assign these so that each of these are turned around and assigned to different nodes. So taking the example that we gave before, we have workload E coming in, and it's mapped, of course, as we had before, but not to the first one, but it's actually to the first and the third in this particular case. And that same poison pill comes in, that same black swan event, takes out the system, and then again, as we expect, takes out the second one. But what we do notice here, and we should point out, is that the partners of the workloads that are adjacent in this particular case are different. So there's a different combination. And so we can see the same thing when we see workload C, who was unaffected, didn't have a poison pill, didn't have anything with it. It's still happy, smiling, everything's great for them, and they're unaffected at the workload level. When we look at it like in the same, and we take the same one here, and we can go to workload D, who's also sharing with workload E, that same failed, one of the, in the failed set. And so we can see workload D comes in here, and it's still working too. So the same problem that we had before, we've really mitigated by being able to do shuffle sharding. And of course, when we go through, we look at the rest of the workloads, they don't care, they were unaffected by this whole thing. And so we can see, in our case here, all of these are green, our 1E is red. Our area of impact is the clients over combinations. Some really powerful math in here.
Yeah, and just like getting back to the math, right? Like if we can add some observations on like what we just discussed over the session, right? If we're talking about like a traditional architecture where we are not like leveraging any sort of like sharding or shuffle sharding, like no cells, nothing like that, if there's a problem, then it's going to probably be like a complete outage, right? So like everyone will be impacted. If we actually evolve and we start talking about sharding, we are actually reducing the impact, and it's going to be localized only to customers that are sharing the same shard, right? In the example that Byron said, and like just taking like the number of nodes, the number of combinations he put together, it would be like affecting 25% of the customers, right? So we are definitely like reducing the impact of like a failure in this application. But if we take like another step back and we are actually talking about like shuffle sharding, which is like another mechanism for us, the impact would be really localized to customers or clients that have the same combination of nodes. So you're like reducing the impact even more, right? Or in the example you mentioned, it's going to be like 12.5% of the customers impacted, right? So you're like really reducing the area of impact by just thinking about like this segregation here, right? And just like adding some more context to it, right? Because we've got this example that had like 8 nodes and like 2 nodes per shard, right? And then we're kind of like having those users like spread across those. But the math is really powerful in that. So if we take actually, we start thinking about like increasing this infrastructure and increasing the number of shards, right? And let's say we are going to like 100 nodes and each like shard will actually have 5 nodes, right? The actually total number of combinations that we can get out of this is 75 million, right? So you can think about like getting like these cards and just like taking like randomly picking like 5 cards, we can get like up to 75 million different combinations, right?
And this is really substantial, right? This changes from a fault isolation or the blast radius. This is pretty significant.
Yeah, it completely is, right? And by the way, if we start like even if we keep going on that example, and if I take like any 5 nodes now, the likelihood of like customers that won't be impacted is going to be 77%. So like 77% of my customers in this infrastructure won't pretty much see anything, right? And in the opposite side, the likelihood of having like 5 customers that are be sharing the same 5 nodes is going to be 0.000, like this lot of zeros, like 13%, right? So we are definitely reducing the area of impact as we start growing our infrastructure, and now we start like changing the way we're applying this sharding, right? So this is pretty much it. And by the way, this is something that we actually do internally at AWS. So if we're thinking about like where we use this, Route 53, Amazon Route 53, for example, our DNS managed service, leverages this exact same architectural pattern, right? So this is basically what helps the service to keep its like very high SLA, right? So this is where it comes from. But I guess at this point, we are really talking about those patterns. We are really talking about how to implement that, but we haven't landed to like a more concrete use case, right? So why don't we do this? Like, why don't we start thinking about like where we would be using it in real life, right? And again, just making sure that those patterns, like when we're talking about cell-based architectures, we're talking about sharding, shuffle sharding, it definitely increases the complexity of the environment. So we don't really want to like have this spread like to all of our applications. We are really talking about those critical applications, right? So this is what we are referring to. And just like taking the example, like let's picture that we have like a coffee shop, right? And me and Byron have it. I was actually going to use a candy shop, but he's kind of like into running and stuff, so told me to stay away from sugar, right? But my coffee shop has 2 different units, right? One of them is in São Paulo, and another one is in New York. And I have like my point of sales, my registers there, and every time that someone comes to my store, they need to pay for something, and they go to like register, and like they start paying, and this is processed by like some sort of backend service, right? In this example here. So imagine that we are just like performing a new deployment, right? And I'm like performing a canary deployment, meaning that I'm not deploying to all my like POSs, all my registers at the same time. So I'm just going to touch one of them, right? And actually what we have like behind the scenes is this notion of shuffle sharding, right? So all of my different like POSs, all my different registers are going like to those different backend services, and they are basically like processing those orders. But like I just did the deployment to POS number 2, to the register number 2, and it was a bad deployment, right? For some reason I couldn't like capture this like on my tests. Something broke down, like, so this is really like one of the failures that you mentioned, like you talked about, Byron. And what actually is going to happen is this is going to impact my backend. So as we can see, 2 servers in this like whole infrastructure are going to be taken down, right? And POS 2 will be unavailable, right? And we can argue that like POS 2 is actually sharing the infrastructure with like register number 8, like POS number 8 and POS number 3 as well, right? And they might be somewhat like affected by that. But because I have shuffle sharding in this example, they won't really be down, right, in this case. Like they are able to still be working. So what I'm saying is that if I have this in my like real life scenario, if I have this like in my store, like I'm just really reducing the blast radius here.
So you're saying I'm still going to be able to get coffee even if the back ends are broken for a particular one?
Exactly that. So like instead of like, if you're like a customer in my coffee shop, you go there and like you're trying to buy coffee, I'm not going to say I can't sell you anymore because like everything went down. I'm basically going to tell you, can you, sir, please go to the register number 3 so I can take your order, like, or register number 1 or like whatever other register I have. So it's really like reducing the impact, and this is how it looks like really in real life, and kind of like a more real life example, right?
So I guess we think about how do we operate these cells?
Yeah, and operations is really like getting to be different when we compare like with the traditional architecture, right? Like, because again, now we are talking about like cells. It's not like a single infrastructure. We are talking about like different deployments, right? But there are like many more things that we need to be aware of and we need to think about, right? So the first thing that we need to kind of like get back to the concepts is we were talking that every cell has a fixed size, right? But what happens if I start like getting my users into those cells, and then one specific user starts like consuming more of my resources, right? I do need to have like some sort of heat management there. So I need to think about like addressing these cases. And again, this is something new that just came like with this notion of cells. It wasn't there before, but we need to address this, right? And really the way of thinking is making sure that we always have a rebalancing or like really a migration tool. So we are able to like take users from one cell to other cells, or even like users that will belong to their specific cells depending on like how much they are using it. And the opposite is also true, right? Because I have this maximum size, and then I might have like infrastructure that no one's using, right? So I do need to think about like load distribution. I need to be smart enough to like evenly get my users across those different cells, like as even as I can, right? So I will be making like an optimal usage of my infrastructure, right? And another thing is, even though we are talking about cells, we are talking about sharding, shuffle sharding, and the objective is really to reduce the blast radius of potential failures in our code or our infrastructure, things can fail. And actually, things will fail all the time. We need to be aware of that. So the notion of high availability needs to be even inside the cells, right? Like cells can fail, the components can fail at any single time, and we need to think about like addressing like disaster recovery, high availability needs within the cells, right? So it's really taking the notion of what we used to do like for a single application, doing this for that single application, but many times as we build more cells, right? And another thing is really thinking about like how the tech stack will influence the management. So the way that I use to manage like SQL servers, relational database, are not going to be the same that I'll be like managing NoSQL database, for example. So being aware of like what's the technical stack, like what are the services, what are the technologies that I'm leveraging, it's very important on this example, right? And just if we can kind of like dive deeper a little bit more, and we can land to like, again, another more concrete example. We can talk about like how monitoring tends to change, right? Because the notion of monitoring that we always knew about is I just want to look at my environment, I want to understand what's going on, and based on that I'll have my metrics, my SLOs, and I'll be able to take actions if something is not like as I expect to be. But let's pretend that one of my SLOs is really like around measuring the latency that my requests are having, right? Before using cells or before using like any of those techniques that we're talking about, I would do like this evenly across all my requests, all my, my servers, all my infrastructure. But now we're talking about cells, so like we have multiple instances. What it means is that I want to be able to understand if there's something wrong with a particular cell. And just taking the metrics from like every single cell and trying to like map my entire like application health out of that might not be a good way, right, of doing it. So we need to be able to understand what's going on at each cell level. We need to be able to understand like how this is affecting the customers that belong to that cell, meaning that it's really like more things that we will need to do. Right, so it's really like additional overhead in terms of management that will come like naturally with the notion of cells and the notion of like these techniques that we're talking. But then, Byron, I actually would have like another question on that. Because we're talking about management, we're talking about the number of cells, we're talking about like how management really changes, right, and some of the complexities that we will get. But really, in the end, is it going to be better for us to have like small cells or big cells? Like, what would be the best approach for us to think about?
Yeah, this is really the crux of the question. It's a really important one, right? So smaller cells, obviously, we're able to reduce the area of impact. The more granular we are, the less customers that we have in there, the less impact. We talked about combinations before, and so that kind of feeds directly into this. It's also, with smaller cells, easier to test. It's a little bit more manageable about what you do. It's really a trade-off conversation, and it definitely depends on whether you know what your architecture or what your workload is, or the criticality of that, right?
Yeah. So basically, what you're saying, Byron, is if I have smaller cells, I'm also like reducing like I'm actually reducing the blast radius of like an eventual failure, right? Because I have smaller cells, it's going to be more cells, but less clients attached to each of those cells.
Yep.
But if I'm talking about bigger cells, it might be easier for me to manage and therefore cheaper. But if something goes wrong with that cell, just because it's bigger and it has like potentially more users attached to it, it's going to like affect more users. So like the isolation is not quite the same, right?
Yeah, and I mean, smaller cells, they're easier to operate, right? There's less to do, right? The stack is smaller effectively. But when you think about this at a cost efficiency level, if I have less cells ultimately, you can think about ELBs or anything else that's in that stack that you're having to deal with and having to provision less of them. And so there's some cost efficiency in that by having larger ones. It's a little easier, sort of, you have reduced splits so that you're not going through and having the situation in which that particular customer or a cell ends up filling up, which is going to cause you to have to move people to another one in order to get the capacity, or if you have failures, to evict people and move them to migrate to another one. And this could be really challenging for those of you who remember VMware and you think about the vMotion and when you're going through and having to quiesce and move that workload in live when you're doing it. It's a very challenging type of piece of software. Right, remember, this is not a piece of software that's given to you. Right? So this is going to be something you're going to be developing when you're thinking about that orchestration and managing those splits and the migration of people in between those cells. And so the system is also ultimately, with less cells involved, from an orchestration standpoint, a little easier to manage as well. Remember, we talked about that routing layer and the amount of cells that are in there, so less complexity in there as well. So that'd be it. Other topics that are really important, right, to consider in this, which is authentication and authorization stuff, right? So how am I doing that? Today, you know, if I'm going to a single stack and managing that endpoint is a little bit simpler. Does each cell have its own SSL certificate where you're terminating the traffic, right? It's a little bit more management there. We've all been through the nightmare of having a certificate that's expiring in a service that fails as a result of that, right? So that's kind of another thing. What are the team boundaries? What's the process, right? So where do our developer teams sit within the organization? So that are they straddled across 3 different development groups and 3 different business units that are contributing to that cells, right? So that's another thing that's going to really make that stack or that individual cell more complex. And how do we network that? Is there VPCs? Is that straddle? What's the network architecture of those things? You know, is that going to be aligned on a cell level? Is that going to be aligned across some other shared between a number of cells, right? So those are pieces. We have, you know, on AWS accounts, is it going to be in a single AWS account? Am I going to break that up per cell? So all of those things are going to be really kind of key things to consider when we do this. So
yeah, so I guess, Byron, like that we are kind of like seeing here is that when it comes about these critical applications, that we are able to implement like a very good mechanism for sharding, or even if we can extrapolate even like more and be talking about shuffle sharding, then we're talking about cells, adding the routing layer, making sure that everything is really resilient. This solution really tends to solve the problem that we were seeing before, right? So this is like, even though adding more complexity, like it comes with the benefit of like addressing the problems that we saw and really helping us like with those kind of like scalable applications as well, right? So I guess that one more thing, like I guess we can kind of like do a quick recap of like everything we talked, because I know it was like a lot of information we were kind of like discussing here today. So let's kind of like go over it and just make sure that those concepts are like well set for us, right? So the first thing is, when we're talking about cells, we are talking about logical isolation, right? And again, tying it back to the bulkhead concept that you mentioned, right? We will be isolating those cells, and if there's a failure, the failure will be contained to that specific cell, and therefore it helps us to really reduce the blast radius. It helps us to really like make sure that most of the environment, depending on what we are doing, can still be working, right? Another thing is really like when we start talking about sharding and shuffle sharding like examples, we understand that there's a very strong need for data modeling, because basically the notion of cells is having everything there. It's like a single instance. So each cell is really like a single instance, and the data is not going to be shared across cells. Right, so we need to understand how to proper model this data. If we're talking about like sharding, we need to understand like what will be like the base for our sharding strategy, right? Are we talking about like customer IDs? Are we talking about like last names? Like, so we need to have like this data modeling effort before we can even start like implementing those patterns, right? And I guess that the third thing is really we'll be aware that when it comes about routing traffic, like and getting into those patterns, we need to build this thing, statically stable routing layer, and that this component is going to be crucial for the working, like for our solution to be working, right? Like pretty much all the requests will be flowing through that, so it becomes like very critical to the whole application, right? We need to think about like building this component. Otherwise, we won't be able to like route those requests.
Yeah, and definitely the need to focus on data modeling. It's really critical. I can't underscore that enough. I think that that's one that we see as a big challenge here, and it really enables you to be able to have shared nothing on the cells. And so, additionally, when you look at it, I think monitoring changes are kind of key, right? So today, we're going through and we're looking at cells, we're looking at services rather at SLO and SLI at an entire service level. But when we're breaking this down, now we're thinking about doing this across cells. So that dimension, the amount of data that we're ingesting and that we're monitoring is huge, is vastly, significantly more than we had before. And so thinking about deployments, today when we do blue-green or we do deployments across, we're going to end up having more cells to deploy across. And so that's a complexity that we don't have today if you're just doing it through a single stack set in region or wherever you're doing it. So that's multiplying that out is definitely going to be another piece. Cell orchestration needs to be implemented, and we talked about that before, right? That's huge. Again, not a piece of software you can buy off the shelf today, so that's definitely some complexity, and that needs to be implemented, and we talked about all those things with routing layers, et cetera, in order to make those. And the other thing that is a key takeaway for me really is extreme resilience can be achieved with shuffle sharding. And so this is like kind of the ultimate when you're thinking about how you want to really build these critical workloads for resiliencies.
All right, and I guess that last but not least, cells are not availability zones and cells are not regions, right? Cells are meant to provide logical isolation. But we always need to think about how we should span our cells across different ACs and even different regions, right? So they walk together, but they are not the same thing. It's very important to understand that the notion of cells is really logical isolation, not physical isolation, right? So this is a very important concept. Another thing as well, and we talked a lot about it today, right? Cells are not necessarily a scaling mechanism. One of the benefits that we get out of implementing cell-based architectures is that it's easier for us to scale the application as we are still getting more users or more clients. It's a matter of scaling out. So really creating more cells and just mapping new users to that. But I would say personally that if your only need is really to scale the application, and if it's not a very critical application or you're not willing to deal with the added complexity, there are other mechanisms that will help you to scale as well, right? So I guess that the message really is, if you just need to scale, and this is the only problem, let's kind of try to understand if there are other better mechanisms that won't bring the additional complexity that cells are going to add to your environment, right?
It's just going to really depend on the application and the criticality, yeah.
Yes, exactly. I would say let's not do this to applications that are really non-critical applications, right? Because it might not be worth, right?
Yeah, and it really does lend itself really to soft state applications more than it is to hard state applications, like DNS, right? Soft state application. Hard state with transactions, maybe not necessarily going to be the best use case for it because it introduces a lot of complexity. If you're willing to introduce that because of the criticality, that's okay as well.
Yeah, and as we're talking about state and soft state or hard state, it's very important to learn that when it comes about cells, data should not be shared between cells, right? So everything that belongs to a user or a client that sits within a cell should stay on that cell. We should not be just sharing data across different cells.
So don't use Dynamo as an example across all of your cells.
Yeah, I guess that the idea would be really, if you have different cells and they are using DynamoDB, you will want to create a DynamoDB table per cell, right? You want to make sure that you are implementing this sort of isolation at every single dependency that your application has, right? And this would be one way of thinking about it.
Just to share nothing ultimately, which is the mantra, right?
That's correct. That's correct. We don't want to be sharing nothing. And then finally, I guess that it's very important to understand that cells have no interdependent logic. So again, we talked a lot about keeping everything that the application needs to be working within the cell. So we are not saying, all right, I have two cells and those two cells are dependent of each other. If this is the case, it might not be really truly a cell-based architecture because it might not give us all the isolation and it might not help us to really reduce the impact for any problems that are happening, right? So basically in this example I talked about, if cell B goes down, it would also affect cell 1, right? So cell A, right? So this is not what we want, right? So I guess that this is pretty much it.
Yeah, and just one quick question. When we were doing this today, I forgot to ask at the beginning here, how many developers do we have in the audience? Just to raise your hands. Okay, great. And I guess the rest solutions architects or architects? Okay, great. Good mix here. Just wanted to get an idea on that. Well, I think that's all we had to say on that one. I thank you for your time today. This has been great talking to you all. And again, some of those people that are here that have been doing cellular deployments or cell-based architecture deployments, maybe you'll join us on the stage next year as we're talking about this. So that'd be great. But thanks everybody for your time.
Thank you all.